should be able to do 5 and 6 and potentially start 7. We'll kind of see. So 5 has only got 3 sections, but it takes a little bit because the skills in there, depending on where you're at and what your level of understanding is to this point, can be difficult. So we'll see if we can finish that before Thanksgiving or not. Probably not, but we'll see. And then I can't remember what 6 is, but 7 is quite easy. Whether that we get that done before Christmas or the first thing after Christmas is fine. But we're in good place. Content-wise, you guys have done a nice job of kind of hustling with me when we've needed to hustle. So I appreciate that. Okay, so section 5.1, we're going to be talking about these fundamental trig identities. So I've consolidated all these identities onto one sheet. You'll see in the chapter 5 on OneNote that we have the basic trig identity sheet here. Now, most of these identities are things that we already kind of know. So like we know that sine and cosecant are reciprocals, right? So sine is equal to 1 over cosecant, or cosecant is 1 over sine, right? Because they're reciprocals. Similarly, cosine and secant and tangent and cotangent, right? Equivalently, we know that tangent on the unit circle is y over x. On the unit circle, the y-coordinate is sine and the x-coordinate is cosine. So tangent is sine over cosine. And if we wanted to kind of rearrange that, you could write it as secant over cosecant, although that's not terribly useful more often than not. And if tangent and cotangent are reciprocals and tangent is sine over cosine, cotangent has to be cosine over sine, right? These are all things that we could, maybe we didn't expressly write these down, but we can infer directly from things that we've talked about quite a bit. The Pythagorean identities, if you think back to the unit circle, anytime you pick a point on the unit circle, on any circle centered at the origin, if you draw the x side and the y side, you're making a right triangle whose hypotenuse is the radius for your circle, right? So in any circle centered at the origin, x squared plus y squared is equal to r squared, where r is the radius for your circle. Everybody's okay with that? On the unit circle then, the x squared is cosine squared, the y squared is sine squared, and the r squared is 1 squared. So we have that sine squared plus cosine squared is equal to 1. Okay. Again, maybe we didn't say that directly, but it's a result directly of things that we have talked about. If I divide both sides of this equation by sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. And 1 divided by sine squared is cosecant squared. That gives me this second identity. And if we had taken the first identity and instead divided both sides by sine squared, divide both sides by cosine squared. Sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. 1 divided by cosine squared is secant squared. That's where that third identity is coming from. It's just a different version of the first one. Is that okay with you guys? Again, we're just trying to do the express version here. Bless you. The cofunction identities, you might have noticed on the unit circle, if you compared, say, sine of 30 degrees is a half, to cosine of 60 degrees, also 1/2. You notice that 30 and 60 are complements. Did you ever notice that on the unit circle? Maybe you did, maybe you didn't. But that's what's going on here with these cofunction identities, is that sine of theta is equal to cosine of the complement of theta. And that's true for all of the cofunctions. So like cosine is equal to sine of its complement. Tangent is equal to cotangent of its complement. Cotangent is equal to tangent of its complement. Cosecant is equal to secant of its complement. Secant is equal to cosecant of its complement. In fact, the prefix co on cosine, cosecant, and cotangent is short for complement. It's like like cosine is the complementary function to sine. Cotangent is the complementary function to tangent. Cosecant is the complementary function to secant. That's what the co stood for. And the last set of identities are these odd and even identities. You recall when we drew the graph, we talked about graphing. The graph of sine was an odd function. Since it's an odd function, we know that f of negative x is equal to negative f of x. That's where this identity, first identity, comes from. And obviously, if sine is odd, its reciprocal function is going to be odd. So the same thing is true for cosecant. Tangent was also an odd function. And obviously, if tangent's odd, cotangent's also going to be odd. Cosine, though, was even. So since cosine is an even function, f of negative x is equal to f of x. That's what we're seeing here. And if it's true for cosine, it's true for its reciprocal function, secant. So that's kind of where these identities are coming from. Let's kind of use some of these here to do some examples. Okie dokie. So let's say we're asked to find the value for sine theta if tangent theta is 3 and cosine theta is negative. And we're going to do this using identities. So we know the value for tangent, so whatever identity we're going to choose to use certainly has to have tangent in it, right? Because that's the only piece that we really know about. And since we know that one of them we're told like the sign of one of them, whether they have to be positive or negative, I would say that I'm almost assuredly going to need to use one of the Pythagorean identities that has like a squared in it somewhere. So I'm going to use that second Pythagorean identity. It says 1 plus tangent squared theta is equal to secant squared theta. Since tangent theta is equal to 3, I can plug that in. If I combine like terms and square root both sides, I get that plus or minus 10 is equal to secant theta. And I know that secant theta is related to cosine theta, right? How are those related? They're reciprocals, right? Secant and cosine. So I can say that plus or minus 1 over the square root of 10 is equal to cosine. And since cosine has to be negative, I know that I can get rid of the plus from my plus or minus. Everybody so far so good? Now really what we're looking for is sine. We know now tangent and cosine. So what I'm going to use is the quotient identity, that tangent is equal to sine over cosine. Since I know both tangent and cosine, I can use that to solve sine. If I multiply both sides by cosine, and then plug that in, so I know cosine is negative 1 over the square root of 10, and tangent is 3. So sine theta should be negative 3 over the square root of 10, or if we rationalize our denominators, which we probably would be asked to do in the directions, end up with negative 3 square root 10 over 10. So that'll be, you'll need to do some of those in your homework for this section. But what we'll do more of are these simplify the expression problems. So in these simplify the expression problems, you're going to start off with something that's kind of complicated looking, and you're going to try to do as much as you can to make this simpler. Ideally, you will want to get it down to a single trig function. That's kind of as simple as things can get. Your tools to do that are going to be basic algebra things like factoring and foiling and distributing and things like that. Making common denominators, adding fractions, that kind of stuff. And the identities that we just described on the previous sheet. So you can do either of those two things at any point, whether it's an algebra trick or apply an identity. On this problem, I noticed that I have two terms, right? Everybody see that? In those two terms, I notice that I have a greatest common factor here. What is the greatest common factor between these two terms? Sine x. So I would begin by factoring that out. Everybody okay with that as a first step? So just did some algebra. There's no more obvious algebra to do though, right? So now I'm going to look for an identity. Is there an obvious identity here? Jackson says P1. So that's the first Pythagorean identity that says sine squared plus cosine squared is 1. So I have sine squared plus cosine squared. So that just simplifies down to 1. And sine times 1 is just sine. And I'm done. Since you can't get any simpler than a single trig function, right? Well, I mean, I guess if it was a constant or something, but let's look at another example. let's say we have secant x minus 1 times secant x plus 1, all divided by sine squared x. Typically, I like to start by looking for any algebraic things going on. Does anybody see an algebraic thing that might be of use? Yeah, so if I look at the top, this looks like a factored difference of two squares, right? Like an a minus b times an a plus b. You guys see that? So I'm going to start by trying to FOIL that out. Everybody good there? Okay. So there's not another obvious algebraic thing to do here, right? So what should I do? Well, I'm going to look for an identity. John? Okay, why don't we just say that why don't we do 1 plus tangent squared equals secant squared? That's maybe a little bit more obvious for everybody to see what's going on. It's fine what you're doing. But I'm going to write it that way because I think it'll be a little bit easier to follow. So what John says is that secant squared is equal to 1 plus tangent squared. It's going to get us to the same spot, John. And I like that because now the plus 1 and the minus 1 can just add to give us 0, right? Everybody okay there? So what I would do next is I'm going to think about this fraction as like tan squared x times 1 over sine squared. And the reason I want to do that is because I'm going to rewrite tangent squared as sine squared over cosine squared. That was one of the quotient identities. If I do that, the sine squareds can cancel. I'm left with 1 over cosine squared. And I know the reciprocal of cosine is secant. So maybe it's just secant squared. Just as an FYI, this was my favorite part of trigonometry when I was a high school student. I loved these little things. They're just like little puzzles. I guess we'll stop here as there's not a lot of time left.